Okay, so what I'd like to do now is get back to the material. Last class, you should have been dealing with, when I was gone, you were talking about basic data structures. You were talking, last class in particular, about dictionaries, which are a particularly powerful set of data, is a particularly powerful data type that supports the following queries: search for a key, and then insert or delete records from pointed to by the data structure, find the minimum and maximum key that is in there, and find the logical predecessor or successor, the element in previous order or subsequent order, okay, that would be there, okay? Any questions about that? Okay, so what I wanted to do now is, now that we understand this thing, last class, Shika supposedly showed you that there is a, using balanced binary search trees, you can do all of these operations in log n time. And the problem of the day has to do with how do you use these operations to do something, okay? And we're going to invent 3 different sorting algorithms, okay, based on the power of the binary, the balanced binary tree. So the first question, it says, is explain how we can use a dictionary to sort in n log n time using only the operations minimum, successor, insert, and search. Okay? This is the only things that we're allowed to use. How can we create a sorting algorithm out of minimum, successor, insert, and search? Any ideas?
I have a question first.
Yes.
Are we assuming that the elements are already in the dictionary?
Are we assuming they're in the dictionary? The answer is no. An important thing is, how do you put them there? Okay? In fact, as you will see, that some of these algorithms would provide fast ways to sort if you didn't count the cost of building. So cost of building is something that does count, right? So how would I use these operations to do it? Anyone want to make a proposal? Okay, yes.
So you could use just insert every number as both the key and the value.
Okay, so what you're first saying is for I goes from 1 to n, insert the, a sub I in the tree, right? So we first have to build our tree, and you're going to use insert to do it, right?
Yeah.
Then, what is the next thing we're going to do?
I would want to use minimum to get the smallest.
M is equal to the minimum element in the tree.
Yeah. And then either keep removing minimum using minimum, or using successor until you get to the end.
Okay, so you want to say keep removing the minimum. If only I had a way to delete things, I could keep removing it. But I don't have the choice of doing that.
Get to the end.
What?
Then we just use successor.
I'm just going to keep using successor. Does everybody see this? I am now going to do something like for I equals 1 to n. Okay? I'm going to print out m, which is my minimum here. I am now going to let m equal to be the successor of m, and keep looping. Okay? I know you can't read it, but this is for me, not you. Okay? But do you see what the algorithm basically is? Build the tree, find the minimum, and then keep looping through, finding the successor after that. Okay? Does everybody agree this is a sorting algorithm? What is the time complexity of this? Well, why is it n log n? I've got to build, okay, rhetorical question. I've got to do the insertion as log n. I'm doing that n times. The tree construction step was n log n. Does everybody see that? Find it, yes?
Why are we assuming it's a tree and not like a hash table?
Well, we're not even going to assume it's a tree. It doesn't matter that it's a tree. What it is something that every operation takes log n time. Okay? So, in fact, I said it was a tree. I have no reason to assume it was a tree, except for the fact that trees are the data structure that does it, right? All I know is I've got those abstract operations, and I've got a time guarantee. And my job is to use the data structure in a way that it does something interesting, right? And now, to find the minimum, how much time does that take? Log n, and I'm paying that once, right? And then 4i goes from 1 to n, print it. How long does it take to print out the current value of m? Constant time per print a step, right? How much time does it take to find the successor? Log n plus 1 is log n. Log n times n, this step takes n log n time. This is n log n plus n log n plus log n. This is order n log n. Does everybody agree? Okay, good. Let's try another way to sort. What if I am allowed minimum, insert, delete, and search? What am I allowed to do this time? Yes? Okay, so what you're now saying is do something that basically for I equals 1 to n, insert to build the tree. Does everybody agree? I've got to build the tree. And now what you're telling me is I'm going to be doing a for I equals 1 to n. In here, I'm going to say m is equal to the minimum element in the tree, right? You're going to print m so that we have it out there, right? And then you're going to delete m. Is that basically what the algorithm is? And what is the complexity of this thing? This part is n log n. This part is n times log n plus 1 plus log n. This part is going to be n log n. Does everybody agree? N log n plus n log n is n log n. Any questions? Yes?
This dictionary has keys and values. What are we finding the minimum on, the keys or the values?
Keys are what we're working on. Again, in general, when you have a data structure, there are keys, which are again, if we think about a data structure for maintaining a telephone book, the keys are the things you can search on. And these might be the names in a phone book, okay, or your ID card number in a university record. Then there's other values that you might associate with the keys in some problem. Here we don't have any problem. We're associated with values we're associating with the keys. We're just sorting a bunch of names or numbers. Okay? So I'm really just interested in the key. Okay? Any questions about that? Or is that clear? Yes?
So how does the insert work then? It inserts the values.
No, it inserts a record with that key in it. Insert. Okay, so what if we go back to the operations? Again, you got to go look at what the operations are. Insert means, we're going to insert a record with a particular element. What I'm kind of assuming the input to that is if this was a tree node, I would have prepared my record. I'm going to have a key field, perhaps some value fields, a left child, and a right child. This is what the node for a binary search tree looks like, right? So insert, I would have plugged my key in here, which is Steve. If I had any particular values, I would do it then. And then I would call insert on the pointer to this thing, right? And the job of the insertion operation is to insert this record into the data structure. So when I say print, I'm really saying print the key field of what I'm pointing to. Any questions? Yes?
So when you, since you're given a task of reading in n numbers, are those n numbers that you're
If I'm reading in n numbers, in this case, if I was using this thing, the n numbers would be my keys. Each number would be a key of a different record. There's no other values associated with that, right? Right now, each number is a number by itself, as is given by the record, right? So I'm asking you to sort n numbers. If I was asking you to sort numbers, ID numbers with students' names associated with it, the values might be the names and the keys might be the IDs, okay? Any questions? Last chance.
Okay, yeah, I'm still not getting the insert of s comma x. X is a key or a value?
S is the set, the data structure. X is a pointer to the node that we're inserting. So in this case, X is the pointer to this thingy that I've built that contains the, the partially filled out record. It doesn't know what the left and right children will be, but this is a pointer to the node that will get filled in the course of the insert operation. Yes? What? How will we keep the tree balanced? This is the job of whoever implemented the tree thing. Last time Skiena should have shown there is this notion of rotations. There are algorithms for what you do on insert, delete, and that force the tree to be balanced by doing rotations. Did Skiena mention these rotations? How many people say yes? How many people say no? Doesn't seem like that. So to force trees to be, there are methods that are complicated that I don't really want to go into that would readjust a tree on every insertion to make sure that it's balanced. Okay? And the presumption of this problem is that whoever implemented it, this particular data structure they're giving you, is implementing a balanced tree. Okay? Yes? Well, that's the time of the balancing is included in the log n. Okay? That's basically what it amounts to. Okay? Any questions? Yes? Okay, so far I haven't used the search operation at all, right? Search operation would be, I mean, they're allowing me to use it, but have I needed it to do it for sorting? So far I haven't needed it, right? Okay? That's my feeling. Okay? Any questions? What is the last one? I'm allowed only insert and in-order traversal. Now knowing about in-order traversal is a good thing, right? We talked about that at the beginning of class. How would I do that? What would be my algorithm for building a tree based on, first I've got to build my tree, so it goes for I equals 1 to n, insert. So I'm going to build my tree that way. And then I'm going to do an in-order traversal, right? And print out the nodes as I went around, right? Bop, bop, print, bop, print, bop, print, bop, bop, print, bop, 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 print, 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 and I'm done, right? So how much time would this algorithm be? I build the tree, it takes how long? N log n. I do my in-order traversal, takes n. This is going to be an n log n algorithm, because n plus n log n is n log n. Any questions? Which of these algorithms is fastest? The answer is they are the same. As far as we keep score, all are n log n, all are the same. Any questions? Okay? So the power of having an abstract dictionary type that can do all these operations in n log n is we can use it in many, many different ways to do many, many different things. And like here, we just tossed off 3 algorithms for sorting in n log n time with very little effort once you have the power of the balanced binary search tree. Any questions? Any questions about the problem of the day? Okay, good. So what I'd like to talk about today is almost a little digression, but it's not. In some ways, it's not. I mean, it's an important subject. It's something on another way to maintain a dictionary, which is a hash table. Hash tables are very, very practical ways of dictionaries, okay? And it's important to understand them because they are very, very practical things. Now, they don't offer good worst-case guarantees. So the great thing about the balanced binary search tree was that all of those operations could happen in log n time in the worst case. And that meant that we could use it to prove that sorting could happen in n log n time. We could use it to do a lot of things. Hash tables have the property that they are practically very, very good. Worst case bounds, you can't assume anything about. Okay? But it is still important to know about them. And it's even more important to know about the idea of using hash functions, because the idea of using hashing and hash functions for things even outside of maintaining dictionaries is a very, very important algorithmic idea. Okay? So, so that's kind of why I want to go through it. The main reason we're going through this is not really to teach you yet another way to maintain a dictionary. The main idea is to get to to understand the idea of hashing, why it works and why it's a great thing to use in different kinds of contexts. Okay? Any questions about what we want to do? So hashing is a technique. Again, if we go back to the earlier slide, what is a hashing? Hashing is basically, well, in the context of the data structure, is that for the data structure of the hash table, the observation is that if we look an item up in an array, give me the 96th item in an array, that takes constant time. And that's great. So if we could find a way to look at a search key and figure out what spot in an array it is, if we could do that in constant time, we would really have something. Okay? And so the thing that's going to drive our data structure, and more important, the other ideas of using hash functions, is this idea that there's a function called a hash function that's going to map a key, okay, or any data object, to an integer. And if we can use that integer as an index to look something up in an array, that would be a very fast thing, right? The idea would be we take our item, we somehow look at it, compute an integer that represents that item, look in that slot in the array, okay, and just grab it. If we can compute that function in constant time, and if the item is actually sitting there at the place where we think it's supposed to be, this should give us a constant-ish dictionary. In principle, usually, but not always. Any questions? Okay. So there's many different ways you can engineer hash tables. And actually, when you guys took your data structures class, did they talk much about engineering hash tables? Who here's? Okay, so hopefully this is stuff you've seen. And there's several ways you could sit down and do it. The conceptually easiest way, in my mind, to engineer a hash table is that you can think of your table as being an array of linked lists. Okay? And what we're going to do is, for every search key, we're going to have a function that maps it to an integer the size of our array. Okay? And that's going to basically specify which bucket your item is in. Skiena, hash, hash, hash. Skeena's number 8. Skiena would go in this list. Jake, chunk, chunk, chunk. Jake hashes to 4. Jake would get tossed into this bucket. Does everybody see that idea? Okay. So to make it work, we're going to have to talk about how we compute that function. That's kind of the most important thing. But if we have a function that will map keys to integers, okay, the way we can build a data structure out of that is this array of linked lists. We use the key, the hash value, to specify what list our item is in. To insert that item, what do? We hash it, get the key, and insert an item into that, an element into the appropriate list with the full key information. It would say Skiena, for example, the key that you have. To look something up, okay? How would we look something up? We compute the hash value of our desired key. That will specify what list is it in. And once we know what list it's in, we're going to do a search of the linked list. Is this Skiena? Is this Skiena? Look for the key that you want. Okay? The idea is that if we have an array of n lists, and our hash function does a good job spreading things around, then on average there's only going to be a small number. There's going to only be, if there's n lists and n items, on average there's only going to be one item per list. If the hash function does a good job of spreading them around, in fact, none of the lists hopefully will have too many items in it. Hopefully they will all have between 0 and 5 items in it or something like that. And if so, then searching through the linked list for which one is actually the one that you want is a constant time problem. Okay? So any questions about how we're maintaining the hash table? Okay? If you have this magic function that maps keys to integers, okay, this gives you a way that will, will give you a fast data structure, provided that hash function does a good job spreading the keys around. Any questions about the mechanics of how a hash table works here? How we're resolving collisions? Okay? Again, there's other ways you would engineer hash tables by, that in practice may be a little bit better, but this is basically the mechanism I want to deal with. Any questions about how a hash table works? Okay, the hard part of what a hash table works is designing the hash function. Okay? And this is where the idea part of the idea part of hashing comes in, especially when you apply it to different algorithms. What is a hash function? We want a hash function that will take an arbitrary string of bytes, or maybe like a string of characters or a string of bytes, and map it to an integer, where that integer is going to be basically an integer between 0 and m. And we want this function to take our string and be fast to evaluate, so we don't spend a lot of time computing this hash thing. And we would like it to be a sort of random-like number, okay? And ideally, we would like it to be that if we're going to say our hash function is going to map numbers between 0 and m, ideally it will use all of those values roughly uniformly. Okay, that's what we would mean by spreading it around evenly. Okay? Any questions about what we want or why? Now, what is my favorite kind of first hash function? The way I like to think, there's lots of different hash functions that exist. The simplest one that I like to think about is I think of the byte string as a big, big number. How would I think of it as a big, big number? Suppose, let's say, it was a string on an ASCII string. Okay, a string on a character set that had 128 bytes to it, possible characters codes to it. So let's say you wanted to hash Skiena. Okay, if you want to hash Skiena, okay, how can we represent this as a number? Okay? You should know from your notion of character codes that the way letters are represented, they are mapped to an integer according to a character code. How many people know what I'm talking about here? Anybody confused by that? Okay? So in ASCII, I believe Skiena A gets mapped to a 32. E probably gets mapped to a 37. N, let's say I'm making this up now, is mapped to a 48. I is mapped to a 43. K is a 46. And S is a 52. Does everybody see that? Every character's gotten mapped to a number, right? How can I make a number out of the whole thing? Well, we can think of it as a base 100, and let's say we think of it as a base 128 number. How would we combine this to think of it as a base 128 number? We would multiply this by 128 to the 0. What is 128 to the 0? We would multiply this by 128 to the 1, which is what? 128. What's this? 128 squared, 128 cubed, 128 to the 4th, 128 to the 5th. Does everybody see that? And by adding that up, we get a number. Does everybody see that? So we can convert this thing into a big number. And for any string, for any sequence of bytes, which is, so for computer things or sequences of bytes, you can convert it to a number. Does everybody see that? Is that number, what you call it, going to be between 0 and m for some m? Well, it's 0 and something big, but there's no upper limit on these things, right? If somebody had a really long name, abracadabra, ba 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 ba, it would be at a bigger number. Does everybody see that? So in order to make this number between 0 and m for any m we can choose, we can take the, the remainder mod m. Does everybody know what the remainder is? The mod function computes the remainder when we divide something by m, right? And if we take the remainder of something mod m, what is the value going to be? The remainder has to be between 0 and m minus 1. Does everybody agree? So what's great about it is that this takes our big, giant number and slaps it down into a small number. Does everybody see that? Now, why is it that this should use, if we take the remainder, why is it that we should be getting numbers generated relatively uniformly? Okay? And my analogy has to do with looking at a roulette wheel. How many people know what roulette is? Okay? This is a gambling game that you go into a casino. Hopefully you won't bet. But if you do, it's this ball. Remember, that what is a casino? It's this wheel with 36 holes in it, right? And what do? They roll the ball around and around and around and around and around and around, and then slowly it's going slower, and eventually it goes skittle, 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 bop into one slot. Does everybody agree? And this generates a random number as far as the roulette wheel, as far as casinos are concerned, right? If it didn't generate a uniform number, people would know to bet on the one that it's more likely to land on, right? Now, what is this thing doing? The distance around the wheel, if we stretched out that path would be this giant long line, right? If we unroll that path. And what is going to determine the actual value? The ball it ends up is basically the remainder when you divide it by the length of the wheel. Does everybody kind of get that idea? So betting on the remainder is kind of hard to predict. It's uniform. So intuitively, this thing should use, if you use this kind of hash function with the right integer as a modulus, so that, and there's some technicalities there. But basically, this should behave like a roulette wheel and give us numbers between 0 and m with equal probability, or something like equal probability, regardless of what keys you give it. Okay? Any questions about that? Any questions about how you build a hash function like this? Okay? Any questions about that? Okay? So what's good about that, if you believe it, is that this gives you a way in time proportional to the length of your key, the number of digits in your key, let's say. If the number of digits in your key was m, this would take order m time to compute the hash code from it. Okay? And if your keys are of constant length, which is what we usually assume, this would mean that in constant time you can compute this hash value. If this thing does a good job of spreading things around the hash table, then in constant time, that the list that you put it in should be small, and so everything should work out constant-ish, usually in practice. Any questions? Okay, yes? What? 2 raised to the I minus 1. Okay, so there is a certain level of, there's a certain level of, there's a certain level of modulus, certain divisors that don't work as well as others. And let me try to convince you of this. You'd like it to be the case that all keys, we use the entire key to to mix it up, right? Let's take it this way. If I took the best kind of a hash function would take your entire key, the entire string that you're using, and they would all contribute to mixing up the numbers. Does everybody agree with that? Now, what happened if, this is to think about, let's say, what the problem might be. What would happen if our modulus was 100 and we were writing out the number as a base 10 number? Okay? Suppose, let's say, I got this base 10 number here, 7, 3, 4, 2, 1, 6, 2, 6. What is the remainder of this thing when you divide it by 100? Does everybody see that it's just the last two digits, right? Does everybody see this is kind of a bad thing if we were going to be using this as a hash value? Because the hash value here is only depending upon the last two digits of our big number and not the whole thing. Does everybody kind of see that? So this is the kind of issue that on the slide I'm talking about trying to avoid, is that if you pick certain bad hash values, modulus values like 100, okay, you're not going to get the result of mixing the entire number. You're just going to strip off a small number of digits from it. Okay? And that's why some moduli are better than other moduli. And this is a technical thing, and we don't really want to go into it. But generally speaking, you want a prime number here. That would be a good thing. And a prime number with certain other properties is the best thing. Any questions? Does that answer your question? Okay, good. Now, the great thing is you guys live in an era for hash tables where they're all built into your favorite programming language, right? You guys don't need to build your own hash table. You don't need to know about that messy moduli that's there, right? You don't even have to know about the hash function, okay? But you should understand it because there's times when you are going to care about the hash function. Any questions? Okay, any questions about how a hash table works? Okay? And again, we have to be aware that certain hash function, a good hash function will be one that will spread things uniformly. A bad hash function will not spread things uniformly. Now, many of you, hopefully all, have social security numbers, not university ID numbers. Everybody think, what is the first digit of your social security number? Does everybody who have a social security number know what their first digit is? Now, that could be, there's 10 possible digits. This should spread people out uniformly, right? Whose first digit of their social security number is 9? Raise your hand. Whose is 8? Whose is 7? And raise your hand aggressively. I mean, be proud of your ID number here, right? Who here is 6? These people are proud. Who here are 5? Who here are 4s? Who here are 2s? Who here are 1s? And who here are 0s? Okay, is this a good hash function or a bad hash function? This is a bad hash function. Okay, why is it? Because everybody got clustered into the same bucket. Does everybody see that? Now let's look at your last digit of your social security number. Everybody think hard. What is the last digit of your social security number? Who here has a 0 as their last digit of their social security number? Be proud of it. Hold your arms up. Who here has 1? Who here has 2? Who here has 3? Who here has 4? Who here has 5? Who here has 6? Who here has 7? Who here has 8? Who here has 9? Okay, is this a good hash function or a bad hash function? This is good. Notice it spread it pretty evenly. Not exactly evenly. Some numbers seem to have a few more. Why is it that the last numbers are, why is this true? Okay, actually I'll tell you why. Okay, it's because of how Social Security assigns its numbers. The first 5 digits of your Social Security number encode basically where you applied for a card and what year you applied. Okay, and all of you come from New York of similar vintage. And that's why you all got stuck in the 0-1 buckets. Okay? And the last digits are described basically in counting order for the bucket. Okay? And this should therefore be, this depends upon the minute you applied for your Social Security card, basically, not where you're from or what the year is. Okay, so this is pretty much random. This is more like the remainder. Any questions? So we want, if we do a good job, a good hash function spreads keys around, okay, and is fast to compute. Okay, and ideally the function I talked about to you should usually be a good hash function. Any questions? So if so, what do we say sort of about the complexity of building this hash table? There are all these dictionary operations. How do we, if we have an m-element hash table, okay, let's think about it. If we have a hash table of the type that I described, okay, where we've got, let's say, m buckets, okay, here we've got m buckets. There are n items that we're inserting into it, 1 to n, right? What is the cost of initializing our hash table to begin with, before we do anything with it? What do we have to do? Is the time complexity of starting out our hash thing? A 1? No. What do we need to do to our hash table at the very beginning when I just allocate a chunk of memory? Yeah?
Would it be n because you have to run the function, the hash function on every that you're
No. Initializing the hash table means that before I insert anything else, what must I do at the beginning? As a yeah? Yeah, you.
You have to clear them all out, so put them all together.
Does everybody see that I've got to basically, this is going to be started out, it's an array of m pointers, right? I've got to nil all of these guys out. Okay? Does everybody agree with that? Right? So before I do anything with my hash table, I've got to actually initialize all the pointers to nil. If not, weird things can happen, right? Okay? But then what am I going to do? To search for something in a hash table, if I have, let's say n is, on the order of m. That I've got the number of items here is about the same size as the number of lists. On average, we would expect there's going to be n over m elements in the ith bucket. That's going to be a short list. If n is approximately equal to m, then this list is going to be small, constant sized. If that's a constant, then this should take constant time to search through. So searching involves, in constant time, compute the hash function of what I care about. Then once I have that hash value, that gives me a list. Once I go to the appropriate list. That list should be, if the number of buckets is roughly equal to the number of items that I have in here, should be of constant size. It should be 1 item, 2 items. The cost of searching through that list should be constant. If we are doing as we expected, searching should take constant time. If we had a lousy hash function, let's say somebody go in there and mucked with your programming language and change the hash function so it output 1 for everything. Then what would the hash table look like? It would be one giant linked list with n elements in it, right? And now the cost of searching through this is going to cost constant order n. Does everybody agree with it? So search, constant expected, worst case n. Insert, well, constant expected. And if I'm here by worst case, here I guess worst case could still be constant, except unless I want to check to make sure I don't already have that item in the list. If I do that check, that's going to take could take linear time. Delete, what's going to happen? To identify the item to delete, I've got to find it. And if my list is of constant size, it'll be constant. If not, I've got a linked list deletion with n items in it, order n time. Any question about those? How would I find the minimum element in a hash table? Let's think about this for a second, because this is maybe not so obvious. If I have an element, a linked list, a hash table with m tables, m lists, and a total of n items in the table, how would I go about finding the smallest one? Any idea? How do I find the smallest one? Yes?
If the linked list is sorted, you could just go through the table.
If they're sorted, that's true, but do I want to sort them? Okay. What? Okay, so it could be, if I maintain the lists as sorted, then I could do the min by just looking at the heads of the lists. And that would be how much time?
Size of the hash.
Order m, because I would have to look at the heads of the lists. In general, it would probably be silly to, I mean, usually if you're computing a lot of mins, you probably shouldn't use a hash table, right? So you're probably not going to maintain it sorted. In general, what you would want to do is to look through every element of every list until you find what the min is. Do you see that if your hash function did a good job, the min could be in any one of these buckets? Does everybody agree? And the only way you can do it is by looking at every element of every list to find what the smallest is. Any questions about that? Same idea goes for the maximum. How would you find the successor to Skiena, okay, in a hash table? You would hash Skiena, or you would keep track of Skiena, but you would again walk over every person, every element in here, and say, are you less than Skiena, after Skiena? And if so, are you the closest to Skiena of all the ones that are after it? The first one that comes by is Zhu. He's after Skiena. The next one that comes by is Yang. Yang is closer to Skiena. I'm going to keep track of that one, right? And the claim would be that after I walk through all of these, the key that is larger than me by the least amount I can find by looking at all the keys, that would be order n. So the search time for all of these operations is order n, because I'm going to have to look at every element. And even if there are there's only one element in the hash table, I'm going to have to look at all m lists. Does everybody see that if I insert one item into my hash table, and I now want to find the min, it's not going to be order 1. I've got to look at all m of the lists, okay, to find which is the one list that has somebody in it. Any questions about that? Okay? So pragmatically, okay, hash tables are a great thing, okay? And in general, the world says you should use them, okay? But for worst case bounds, which is what we're going to specialize in this class, we are going to be typically thinking in terms of binary search trees. Any questions? Balanced binary search trees. Any questions? Okay. Any questions about hash tables? I'm going to stop talking about hash tables right after this and talk about other cool things you can do with hashing. Okay? But any questions about hash tables? Yes? Yeah. Okay, you're saying, why don't you keep track? Okay, so the point here is a question of, can you make use of anything except the remainder? Could you use the whole number here somehow? There are a couple of different issues. First, note that the whole number is a big thing. And you don't probably want to, it's kind of messy to work with, so you probably don't really want it, okay? We like the remainder because the remainder is this nice number that's exactly the size of our hash table. But the important point is that once we have a table like this, no matter what data you have in the linked list, if you've got to search all the elements in the linked list, it's going to take you order n time. Do you see that if you have a linked list, because you can't get anywhere except to the next element, there's no extra information that could help you search that faster? I guess if it was sorted, it could tell you when to stop. Okay? But you see that in principle, once you've got a linked list, okay, we have a bucket, forms a linked list. Within that linked list, basically there's nothing you can do. You have to walk through it, okay, unless you really have a stopping condition. Any questions? Any other questions about hash tables? There are other data. Let's say I don't want to talk about this right now. So there are. If you want, you can talk to me afterwards if you want. Okay. But we can talk about. But for the purpose of what we're doing in general, we're only interested in the remainder for the hash function. Any questions? Any other questions about hash tables? Okay. So now remember hash tables, but put that aside for now. What is wonderful is that there are, hash tables hashing is useful for a lot of different things, especially in internet scale things, okay, than just maintaining dictionaries, okay? So for example, one problem that Google has to do fairly often is, there have got to be a zillion copies of Wikipedia on the web, okay? Or let's put it, somebody has a picture of a cat they send to a friend, and this spreads and becomes viral. It's often the case that on the internet, there are many, many copies of the same file. Does everybody agree with that? And it would be bad for Google if it didn't know for any particular text content, what is the original, or what is one representative of it. It would like to sort of keep only a unique copy of every single file on the web. Does that kind of make sense? So when Google has its crawler and crawls a new page, how can it figure out whether or not this page is one it has never seen before? Okay? It could go compare it to the entire internet and say, is this the same? Is this the same? Is this the same? That would be expensive. Does everybody see that? What does Google do? Google takes each new document and computes a hash code. Okay? The whole big web page gets crunched down to a small hash number, right? Small meaning 128 bits, 256 bits, okay? And then all that Google keeps is a table of the hashed values of every document it has seen on the web, okay? If 256 bits is enough, that it's very unlikely that given how many web pages there are in the world, okay? Most of these hash codes won't correspond to real web pages, okay? What does Google do? It takes the new page in, it computes a hash code of it, it checks to see, have I seen this hash code before? If so, I have presumably seen this page, okay? And it doesn't even bother to look at the page anymore, just immediately throws it out. Maybe there's going to be a few new web pages that are unlucky enough to hash to a value that was already there. But almost always, if you have a big enough space of hash codes, the new page that comes along, okay, if it hashed to something that was already there, the only way it did that was by being the same number, the same page. And so by maintaining this, it can identify duplicates, okay, on the web very, very quickly. How many people understood what I just said? I don't think I said that as clearly as I liked it. How many people want me to explain that again? Okay, enough people. Let me try that quickly. So what is Google's problem? Google's problem is that it has a, every day it's scanning a new document. It's got billions of documents. When it sees a new document, has it already been seen before? What does Google do? It builds a hash table on, let's say it hashes every web page. Here's a web page. Gets hashed to a 256-bit integer. Okay? Given the number of web pages that are out there on the world, there are much less than 2 to the 256 different web pages. Does everybody agree with that? How many web pages are there in the world? 1 billion? 10 billion? 100 billion? But that's small potatoes compared to 2 to the 256. Does everybody agree with that? So this means that almost certainly, if I give you a number between 0 and 2 to the 256, it corresponds to a number that does not exist with a hashtag, does not correspond to any page on the web. Does everybody agree with that? So what does this mean? Let's say that somebody has put an illegal copy of Skiena's book somewhere on the web. Okay? Then, what does this mean? This will get hashed to some long number, 256 bits long, right? Somebody else puts a copy of Skiena's book illegally on the web. That will get hashed to the exact same thing. Does everybody agree with that? And that therefore, when you go to this position, the fact that when you scan the second copy, the fact is that that number has already been used is enough to tell you, I have already seen this file, almost certainly. There is a small chance that, let's say, Joe Mitchell's web page, he was the guy who taught here before me, let's say his web page might accidentally hash to the same number as my book. Does everybody agree with that? But the odds of that are very, very small because we've got such a big search space and such a small number of web pages. But what could Google do? It could then say, oh, wait, is Mitchell's page really the same as Skiena's book? Or more likely, it would just assume that that's the same as Skiena's book and throw it away. Okay? And it's justified in doing it because the probability of a collision is so low. Okay? Any questions about how we're using this? Okay? Does everybody see how a hash code is a good idea to do it? And you're taking the hash code not on something, name-sized, but Skiena book-sized or file-sized on the internet. Any questions? Okay, so that's a good example. Now, let's say that somebody wanted to plagiarize a document. You can imagine a kind of a problem where, again, many of you know that when you submit your programming course in the introductory courses, does the teacher take your programming assignments and run them against a plagiarism detector? How many people have heard this? Right? How can they do this? Okay? Let's think about how we could build a plagiarism detector for your programs, right? How could we use hashing to quickly detect whether there's any plagiarized programs, okay, in a particular class? What might be the way to do it? Okay? Yeah? Okay, let me sort of, so the first thing we could do is the same kind of thing that Google would try, right? It takes every program and then hashes it, right? It gets a hash code for it, right? And again, if two programs hash to the same value, then we know that they're probably copies of each other, right? So does everybody see that this is a great way of identifying exact duplicates? But what would the bad student do to try to avoid getting detected by this plagiarism detector? Yeah? Change a variable name. You've tried that before, I guess, all right? Okay? So maybe what they're going to try to do is make a little change in the document. Does everybody see that if you make one change to one character in that document, the hash code changes? Okay? Remember, think about that, the consequences of taking that big number and hashing it down to the remainder. One tiny change is going to give it a different hash code. Okay? And something especially as big as changing all the variable names, right? That sounds like that's even going to be, he's going to beat it, right? What are we going to do? The plagiarism detector, first of all, what it's going to do is instead of hashing the entire document, it's going to hash strings, take short fragments of the program, and hash each short fragment separately, right? The first 20 characters of your program, the next 20 characters, the next 20 characters, the next 20 characters, right? And now you're building your hash table on fragments. And whenever a program has a fragment that collides with another program, it's a possible suspicion. Does everybody agree? And if I find that my program collides with his program on 25 fragments, that might be enough to say, and we'll go back and look, and he changed all the variable names, right? And in fact, what I probably should have done before I even did this thing is change all the variable names to nothing. Just sort of remove all variable names before I even did this hashing thing. So I would nail this guy without that. Does everybody kind of see that? So by doing those transformations and hashing the pieces, does everybody see that if I see enough pieces that match, I get suspicious, and I can then do the check? Okay? Any questions about how this works? How people get the idea now? Okay? And again, you have to optimize how long a fragment do I use and what kind of pre-processing do I do to make it more likely I'm not going to get fooled by some simple transformations he's going to do. Okay? But basically, this is how these plagiarism systems work. Any questions? Okay? Now, how can I convince you that a file doesn't change? Okay, this is a separate interesting application of hash functions. It turns out to be kind of important. Sometimes, let's say, I would like to know whether or not I give you a file. Okay, I look at it for a while. I don't want to store this file. But I'd like to know later on whether or not it has changed or not. Okay? How can I do this test kind of efficiently? So I kind of believe that you're not, I have this big long document, Skiena's book. Let's say you want to see when Skiena's going to come up with another edition. Okay? I don't come up with editions very often, right? How could you tell whether your edition of the book is the same as my edition of the book? Okay? Well, if we compute the hash value of my book and the hash value of your book, if they're the same, they should stay the same. If these hash codes ever change, that's a sign that the file has changed. Does everybody see that? Okay? So there turn out to be a bunch of different cryptographic applications that revolve around the fact that, that I can send in a hash code representing a file. And you can be sure that when I later show you the real file, I didn't change it. Okay? So let's talk about a specific case. Let's say we were going to have an auction. Okay? And you want to send in a bid. Okay? And you want everybody to see what your bid is. I want to make, okay, let's say I'm going to have an auction. Okay? And I want you to, I'm going to try to auction off maybe this file here. And you have to give me a price that you're willing to pay for it. Okay? Now, if you know what everybody else is bidding, okay, does everybody agree you would bid just a tiny bit higher than that? So I want to collect all the bids from people without them making their numbers readily readable, but be sure they won't change it afterwards. Can you imagine why I'd like to do this? I'd like to collect everybody's bid. I'd like to be able to be sure I can commit you to your bid, okay? And that you're not going to change it, but I don't want you to send me the actual number because maybe other people can read it. Do you kind of see that? So what if before the deadline I make you send me a hash code of your bid? You type your bid on a sheet of paper, and I ask you to give me a hash code of that, right? You send in to me the hash code of what your bid was. 7294. Okay? So from all the bidders, I get the hash codes of their bid. And then there's the deadline. And now I say, email me your real bid. Okay? Now, none of these guys can change their bid. Does everybody see this thing? When they email me their real bid, okay, the thing I'm going to do is to make sure that the hash value of that is the same as the hash value they sent me. Does everybody kind of get that idea? So this way I can be sure that the number that they're sending me now is the same number they were sending me before. Only now I can read it, and there's no danger for everybody in me reading it. Any questions about that? And this works so long as you've got a hash function that you can't go, given the hash function, figure out what the original submission was, inverting the hash function. Any questions about that? Yeah. The hash function, let's say, is public, yes. So everybody uses the same hash function, okay? But they're sending in the hashed values. I can't, if it's a decent hash function, I can't go from this and figure out what it was that they had, right? But if it's a good enough hash function, you can't come up with another message that will hash to the same value. So I know that what you send me later has to be the thing you had before. Any questions about that? So there are a lot of examples of hash functions in action, where, which can do these kinds of things. Any questions about hash functions and cool applications for hash functions? Okay? This is a good and important thing to know about. Any questions? Let me go through very, 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 very quickly a very, 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 very cool application of hash functions. Okay? So if you're saying, oh, I'm tired and I'm going to get confused, forget about it. Close your ears quietly and you can walk out later. Okay? But let me show you there's a very cool application of hash functions to the problem of substring pattern matching. Okay? So let's just make sure let's try to understand the problem here. One is you were given a long pattern text string and you're given a pattern string. This is something you should be used to doing in text editors, right? Have you ever been in your text editor? You say, oh, where in the file is this? So a common problem is substring matching. The input is a long text, let's say the Bible, and you'd like to give it have a shorter text, which is the pattern. And you want to ask, does this pattern exist in that text? Does everybody see what the problem is? So you can imagine this is the Bible, this is Skiena. Is Skiena in the Bible? How would you tell? Give me an algorithm now for solving this problem. The problem, remember, is I've got a long text T and a shorter, but still possibly pretty long pattern P, and I want to know, does this pattern exist exactly in the text? How would I do this? Okay, yeah? Check all possibilities. Does everybody see this thing? I could say the first 6 characters of the Bible. Is that Skiena? No, it's not. Then check the next. Is the 2nd through 7th character of the Bible. Is that Skiena? No. 3rd through the next one? No. Yeah?
We can improve this slightly by looking for S, and then when we match S, we could try the rest of it.
Okay, so there's certain things you can improve with little diddly things, okay? But does everybody see that, in principle, let's think, what is the worst case of this algorithm? Again, the reason, not to dismiss it, but when we think about worst case analysis, is it order n? If this pattern was of length n, and this pattern was of length p,
we could make it happen in ON.
could you make it happen in order n? Not really necessarily by doing it the way that we did. Suppose my pattern was E with an like that, and my text was all E's. Okay? Does everybody see that I would go E, 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 E? Oh, mismatch. Slide it over. E, 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 E. Oh, mismatched. Does everybody see that? So what would the time of that be? If this was of length n and the pattern was of length m. Does everybody see that this thing of brute force should be n times m? How many people see that? How many people don't see that? Okay? And again, why is it n times m? Because in the worst case, when my pattern, the text was all the same characters, and the pattern was all the same characters except something at the last element, if I start matching from the left, I'm going to have to check all m characters before I decide the pattern didn't match. And then I slide the pattern over one, and I have to check all m things to decide it doesn't match. I'm doing that n times, each time taking m, right? So the normal worst case of the brute force would be n times m. And you can do certain heuristics and maybe things, but that's not going to change the worst case time. Okay? Let me give you just a kernel of an idea behind how you might be able to use hashing to do this faster. One thing we note is that we could compute a hash code on the pattern. Does everybody agree with that? Now, what if I find a set of characters here of the same length and I compute their hash code? If the hash code of the pattern differs from the hash code of that window in the text, does the pattern exist there? If the hash code of the pattern was 75 and the hash code of this particular window in the text was 103, is it possible that this pattern existed in that window of the text? No, because if so, they would have the same hash code. Does everybody agree? And if the hash code here was 75, does that mean that this pattern equals that part in the window? Possibly, but not necessarily, right? But if the hash code is done rarely, if this hash number is big and random, it's relatively unlikely it's going to occur by chance. Does everybody agree with that? So we can imagine the following method to search through a string. Compute the hash code of the pattern, then compute the hash code of the first window. Does it match? If no, slide over and compute the hash code of that. Does it match? No. Slide over. Does it match? Yeah. Well, let's check it explicitly. Okay? And it should be very, very rare that the test explicitly, that the hash codes match and the strings are not the same. Does everybody get that intuition? And if you combine those ideas, that gives you a way to search in order n time. Build the hash code here, okay? Do the hash code, compute n hash codes here, okay? Does that hash code match what it should be? Okay, each of those should be constant time. This kind of an idea leads to an order n test. I encourage you to read the slides to see how I did it, because it's a little